All right, baby. Looks like we're live. Let me fix the mic position real quick. Somewhere there. All right, everybody. So in today's video, we're gonna continue on with the chemistry series. And if you want to learn chemistry, all you got to do is just watch the video. And let's pull up our chemistry notes after we get that going. Hey, Randy, thank you for joining. Today we're gonna continue on with the chemistry. Today we're at Avogadro's number, and mostly when high school kids, they spend a lot of time right here, and honestly they probably shouldn't spend all their time there. Hold on, I'm trying to pull my notepad out real quick. Hold on. Okay, I think I got it out. I think this is the all right, so that's where we left off last time, I think. Calcium nitrate. Yeah, calcium nitrate up there. Okay. What it do? Hey, but Randy, thank you for joining. I know everybody's always busy, but any amount of time people spend here, it really helps a lot. Awesome. Thank you. All right, so let's get started with the. And remember, I do all the work. I'll solve everything, and if you guys have any questions, always let me know. And let me know how the mic sounds. If you hear like an echo or something like that. All right, but anyways, let's keep reading. All right, so even this Avogadro's number and the mole, section 3.4. Let me take off my glasses real quick. Oh wait, let me turn on some more lights real quick. All right, there you go. I don't know if it mattered, but I just turned on more lights so we could see the book a little bit better. All right, so let's go. 3.4, Avogadro's number and the mole. Even this, I thought that was a hair, but it's a pencil mark. Even the smallest samples we deal with the laboratory contain enormous numbers of atoms, ions, or molecules. For example, a teaspoon of water, about 5 milliliters, contains 2.3 2 times 10 to the 23 water molecules, a number so large that it almost defies comprehension. Chemists therefore have devised a special converting unit for describing such large number of atoms or molecules. In everyday life, we use counting units such as dozen, 12 objects, and a gross 144 objects to deal with modestly large quantities. I never heard of gross, but I've heard of gross income and shit like that. 144 objects. Interesting. Let me know if anybody uses that. In chemistry, the unit samples is the mole. That's what I use. Abbreviated mole. A mole is the amount of matter that contains in many objects, atoms, molecules, or whatever objects we are considering. Wait, I know. Considering as the number of atoms in exactly 12 grams of isotypically pure 12C or carbon 12 from experiment. Scientists have determined this number to be 6.02221 times 10 to the 23rd. Amedeo Avogadro, 1776 to 1856. Avogadro's number has the symbol N with an A which is we usually round to 6.02 times 10 to the 23 moles minus 1. I'm not sure what that, the unit mole minus 1, inverse mole. Okay, there you go. Inverse mole per mole reminds us that there is 6.02 times 10 to the 23rd objects per 1 mole. A mole of atom, a mole of molecules, a mole of anything else all contain Avogadro's number of these objects. And sorry guys, if I can't read sideways, it's kind of hard for me to read sideways. So when I go down, sometimes I reread the same sentence, and I try not to. Okay, so a mole is 1 mole, 12 carbon atoms. I should probably just read from the computer. All right, so 1 mole, 12 carbon atoms. Basically, all it's saying is that number's important, and all it says a mole is that amount of anything. So it doesn't matter if it says 1 mole of electrons or 1 mole of whatever. It's always talking about that number, 6.02 times 10 to the 23rd. And that number is really important. Let me let's get the sketch out, but this number is really important, 6.02 times 10 to the 23rd. All right. So, and if we write it out, if you want the longer version, if you want all the numbers, it's 6.0221421. All right. So this number, a mole is the amount of matter that contains as many objects or whatever objects we are considering, as the number of atoms is exactly 12 grams of isotopically pure 12 carbon. The experiment scientists have determined this number to be 6.022. Okay, so somehow I gotta ask the professor what the fuck, but I think this number they derived it from carbon, but I'm not sure. That's what the book's saying, right? Anyways, let's keep going, guys. And thank you, Randy, if you're still here. Thank you so much. All right, let's flip the page. And remember, guys, there's a strategies of problem solving. I'm not gonna read that because I'm just gonna do the work for you. But believe me, when you're reading, when you guys are doing, because this is a university level textbook. This is not a high school textbook. So we're barely in chapter 3, and most high school students are probably like halfway through their semester or whatever. I forgot how they do it. Yeah, semester, right? Halfway through their semester or almost ending their semester. They should be like around December. Yeah, they should be around. All right, so in a few days, we did as much high school work, or were the high school kids, until they reached December-ish, and probably around their midterm or their finals, probably up to like chapter 4, because I saw, yeah, maybe up to like chapter 4, and we're already. Anyways, let's just keep going. Avogadro's number. All right, so this is our first problem, and ahorita bubbles. My dog wants to eat. Okay. All right, Avogadro's number. Avogadro's number is so large that it's difficult to imagine. Spreading 6.02 times 10 to the 23rd marbles over the entire surface of the Earth would produce continuous layer about 3 miles thick. In Avogadro's number of pennies were placed side by side in a straight line, they would encircle the Earth 3 trillion, 3 times 10 to the 14th times. Okay. Estimating number of atoms without using a calculator, arranging the following samples in order of increasing numbers of carbon atoms: 12 grams of carbon, 1 mole of C2H2. I'm not sure what that is. It might be no. I'm not even gonna say sugar, but or whatever it is. I don't know what it is. So C2H2 and molecules of CO2. All right, so all right, so it doesn't matter what it is. Oh, let me take out my. All right, so it doesn't matter what it is. So they're talking about grams, right? And then they're talking about molecules. Oh shit, I put moles. And then you got moles, right? All right. So it doesn't matter how many grams you really put. Okay, hold on. Let's put them in order. Okay. So you know molecules? Molecules is the smallest one from right here. So my bet would be like this is the smallest one. And then grams is a large amount of molecules. So let's say this is number 2. And then this is my best bet is this is number 3. Because moles is the biggest number. You see that? But we won't find out until we actually see 1 mole and molecules, 9.6 something molecules. Yeah, I said that's my final answer without really going through the book. All right. So that's my thing. So that's how I would arrange them. So you see how it says 12 grams of carbon, 1 mole of C2H2, or 9 times 10 to the 23rd molecules of CO2 gas. Well, actually, it just says CO2, so it could be solid, so it doesn't matter. So just say of carbon dioxide, and like I said, I'll just put them in order. So I know molecules is the smallest, and then followed by the amount of grams, and then moles. I'm assuming that's the biggest one, but let's go check it out. Uh, all right, above. And we didn't solve it, but I'll just write the answer that they gave us. All right, so they put it in order of 12 grams of carbon is the smallest. I think this is. Wait, this is so weird. How? Wait, yeah. So they put 12 grams of carbon is the smallest one. Oh yeah, so I am right going so far. So 12 grams of carbon is going the smallest one, and then mm-mm. And then the molecules. So CO2 molecules, whatever the thing was, CO2 molecules, and then followed by the moles. All right, sorry, I'm gonna rewrite that. So it was the grams first, and then followed by the molecules, then followed by the moles. So this is the answer they gave us, but let's go check back what I said. I said molecules first. Oh, molecules was not first. See, like I said, we didn't solve it. We just went whatever we thought, and then moles was last. Either way, moles was last. Fuck it. All right, let's do our first problem. That's actually a problem. All right. All right, converting moles to number of atoms. Calculate the number of hydrogen atoms in 0.35 moles of C6H12O6. All right, so okay, let's go. All right, let's write down everything we know. We're like, I'm getting stuck. Just like you, I have to remember all this shit. All right, so it's talk. The question is, let's write down what the question is. The question is number of hydrogen atoms. You see that? And let's put what we know. We know we got 0.350 moles of C6H12O6, right? That's the given. So let's write that number down. So we got 0.350 moles Wait, usually when I do chemistry, I like to write the number first. The C6H12O6 moles of that shit. All right. And remember what 1 mole? So 1 mole is equal to the Avogadro's number, 6.02 times 10 to the 23rd molecules, because we're converting to molecules now, right? And then for molecules, we want to find out what 1 molecule. Let's continue this way. 1 molecule fuck it. 1 molecule of C6H12O6. See that? So 1 molecule of this has 12 hydrogens, because we want to figure out how many hydrogens is there. See that? So 1 molecule of this has 12 hydrogen atoms. But you see that? And then this is going to give us our equal sign. This equals. All right. So the way to solve this is, remember, we multiply all the numbers from the top together. You see that? Divided by all the numbers in the bottom together. Okay. So how does that look? So it's going to be 0.350 times 6.02 times 10 to the 23rd times 12. I'm put 12 over here times 12. See that? All those numbers multiplied together. All right. And then now you multiply all the bottom ones together, which is 1 times 1. Okay, see that? Which is 1 times 1. And then when you multiply that on the calculator, so all these numbers multiplied together divided by all the numbers down here together. Okay. So that's going to equal. So when I plugged it in my calculator, when I plugged it in, I got let's write it. Let's write the whole thing. 12.350 6.02 times 10 to the 23rd times 1. So when I plugged it in, so when I plugged this in, guys, I got 2.52 times 10 to the 24. See, I did it on my book right here to the side. Oh, shit. See, I'm doing this whole thing. I'm not even showing you. Fucking dumbass. What the fuck? Nah, maybe I should do this whole thing all over again. All right. Anyways, guys, so I took what I knew. See that? That's gonna suck. Let's do the next problem. But that's the answer right there. On the book, they got 2.53 times 10 to the 24 hydrogen atoms. Okay, 2.52. I know. If I would have gotten the remainder of the numbers, I would have probably rounded up, but I didn't. So that's where I got. But anyways, let's go to the next one. You see where it says practice? So we're definitely going to do this one. All right. So how many oxygen atoms are in 0.25 moles of calcium nitrate and 1.50 moles of sodium carbonate? All right. So, oh, you see this one's a perfect saltwater question for people that do, or even freshwater for those that do this. All right. Wait. First, let's see how far I have to go before this chapter ends. There's a lot of math in this chapter. All right. So anyway, let's do this problem. Now you guys can see what I'm doing. Okay, so let's go. So how many atoms of oxygen? So oxygen, they're trying to find out how many atoms of oxygen in 0.25 moles of calcium. Of calcium nitrate. All right. So that's the first one. All right. So you can see the answer. It says 9.023. But we're gonna have to figure out how did they get that number. Okay. So first off, we got what we know is 0.25 moles of calcium nitrate. You see that? 2 moles of calcium nitrate. And remember, 1 mole. So this is going to cancel the moles right here. So 1 mole is equal to 6.02 times 10 to the 23rd. So remember Avogadro's number shit. Molecules. Okay. I think I got to figure out something. I'm just going to put MC for molecules. Okay. So molecules, right? Of, what is this? Of calcium nitrate. Well, we know it's calcium nitrate because I'm just going to say we're talking about it right there. Of calcium nitrate. All right. And then we got to put molecules here. So molecules. So one molecule of calcium nitrate. Shit, I can't. Okay, so one molecule of calcium nitrate has oxygen. So has two oxygen. You see that? So it's two. Oh wait, that's a lie. It's 2 times 3, so it has 6 oxygens. So times 6 oxygen atoms. Oh, 6 oxygen molecules. Yeah, you could say molecules or atoms, whatever you want to call it. The reason, because we're only talking about oxygen, and oxygen is never alone. It's usually combined with another oxygen, so they call it O2. And really, that's a molecule. That's not an atom. An atom would be just the individual oxygen. See what I mean? But anyways, that's just some shit. That's a little bit obvious, but not so obvious if you're learning. All right, so now to solve this, remember we multiply all these numbers at the top together, divided by all the numbers that you get when you multiply them together at the bottom. Okay, so what would that look like? That's going to look like 0.25 times 6.02 times 10 to the 23. See that? Times 6. All that times 1 times 1. See that? Which equals 1. I don't know if I should just put 1 or 1 times 1. You see that? Because of these two numbers right here, they're only 1. All right. So when you put an equal sign, what you get is 9.0. Oh shit. Times 10 to the 23rd oxygen. I'm just gonna put O2. Okay, see that? So when I plugged it in the number, in the calculator, that's what I got. Sorry, I don't have a calculator with you guys, but that's what I got. Okay. And then for part B, which it says 1.50 moles of sodium carbonate. Sodium, Na, and carbonate is CO3. First off, you got to know this is the sodium carbonate. I'm trying to figure out the charges. Carbonate, hold on, let me look at the periodic table. Yeah, so sodium has a 1 charge, and carbonate apparently has a 1 charge also. Mostly because if you look at the calcium has a +2 charge on the periodic table, and sodium has a +1 on the periodic table. So I'm assuming this is a -1. Oh shit, a -1. But I'm just assuming. All right, guys. So first off, the answer's right there. You see that? The answer's right there. But let's see if we get the answer of 2.71. All right, so let's go. So let's get what we know. Oh, they want to solve for they want to solve for oxygen atoms. They want to solve for oxygen. All right, so we got 1.50 moles of sodium carbonate of sodium carbonate. All right, and 1 mole like I said, guys, I'm just repeating the same shit over and over. All right, so 1 mole of sodium carbonate. All right, so sodium carbonate has 6.02 times 10 to the 23rd molecules. All right. And the reason you want to go from molecules instead of atoms, even though you could say atoms, is because, I mean, atoms, you'll get it wrong. But the reason you say molecules is because this is a molecule. And then after you break down the molecule, you want to figure out the exact one you want to figure out, whether it's oxygen, carbon, or the sodium. All right. It doesn't really matter. All right. Equals sodium. I mean, molecules. And then one molecule of sodium carbonate has 3 oxygen atoms. Has 3 oxygens. You see that right there? Just by definition of what you should know what carbonate is, CO3. See that? And then again, you get 1 times 1 equals 1. All right, so we're gonna now that's the answer, right? Then we get the number. So then you get 1.50. All right, you see that? Times. I usually don't like to put an X, but I'll put an X right there for multiplication. Yeah, let's not put an X. Times 6.02 times 10 to the 23rd. This is why I don't like to put the times, because you see how it's a X right there for the 10 times 3. Okay. All these numbers right here divided by this. When you put a fraction, it means division. All right, divided by 1 times 1, which is 1. And then your answer should be 2.71 times 10 to the 24. Okay, and that's how you get that number. Bam. All right. So that's how many of oxygen. All right. And that's pretty much it. All right, so molar mass. I think we're almost done with this chapter, guys, and we're 33 minutes in. God damn, dude, that's a lot. All right, but fuck it. Molar mass. A dozen, 12, is the same number whether we have a dozen eggs or a dozen elephants. Clearly, however, a dozen eggs does not have the same mass of a dozen elephants. Similarly, a mole is always the same number, 6.02 times 10 to the 23rd, but one mole samples of different substances will have different masses. Compare, for example, 1 molar of carbon 12 and 1 mole of magnesium 24. A single carbon 12 atom has a mass of 12 atomic mass units, where a single magnesium 24 atom is twice as massive, 24 atomic mass units. To two significant figures, because a mole always has the same number of particles. A mole of 24 magnesium 24 must be twice as massive as a mole of carbon-12 because a mole of carbon-12 has a mass of 12 grams by definition, and a mole of magnesium-24 has a mass of 24 grams. This example illustrates a general rule relating the mass of an atom to the mass of Avogadro's number, 1 mole, of these atoms. The mass of a single atom of an element in atomic mass units, or in AMU, is numerically equal to the mass in grams of 1 mole of that element. The statement is true regardless of the element. One atom of carbon-12 has a mass of 12 AMU. 1 mole of carbon-12 has a mass of 12 grams. One atom of chlorine has an atomic weight of 35.5 atomic mass units, or AMU, equals 1 mole of 1 mole of chlorine 1 mole of chlorine has a mass of 35.5 grams. One atom of AU, I think it's gold, has a weight of 197 atomic mass units, and 1 mole of AU has a mass of 197 grams. And I think AU is a gold. Notice when we are declining with a particular slope isotope of an element. Notice we are dealing with a particular isotope of an element. We use the mass of an isotope. Otherwise, we use the atomic weight of the average atomic mass of the element. So basically, it's saying if it's an isotope or a different version of the same atom, use the isotope atomic weight instead of the normal weight or the average weight. For the kinds of the substance of the same numerical relationship exists between the formula weights in AMU and the mass in grams in 1 mole of that substance. One water molecule, one H2O molecule has a mass of 18 AMU. 1 mole of H2O has a mass of 18 grams. One nitrate ion has a mass of 62 AMU, and 1 mole of nitrate has a mass of 62 grams. 1 mole of 1 mole of sodium chloride or salt has a mass of 58.5 atomic mass units, equals 1 mole of sodium chloride has a mass of 58.5 grams. Illustrate the relationship between mass in a single molecule of H2O and a mole of H2O. Which has more mass, a mole of water, H2O, or a mole of glucose, C6H2O6? Glucose, obviously. Which contains more molecules, of a mole of water or a mole of glucose? They both contain the same amount of molecules. When it says give it some thought, oh, sorry, you guys can't see that shit. So in give it some thought, where it says which has a more mass, a mole of water or a mole of glucose? So glucose has more mass. Which contains more molecules, a mole of water or a mole of glucose? That's a trick question. A mole is a mole, and they both have the same amount of molecules. It's like saying what weighs more, the feather, or a pound of feather, or a pound of rocks, or some shit. All right, the mass in grams of 1 mole of substance, that is 1 mass in grams per mole, is called a molar mass of a substance. The molar mass in grams per mole of any substance is always numerically equal to the formula weight in AMU. The substance sodium chloride, for example, is a formula weight of 58.8 atomic mass units, and a molar mass let's fix this real quick. All right, so it has a molar mass of 58.5 grams per mole. For further examples of mole relationships is shown in table 3.2, figure 3.9 shows 1 mole quantities of several common substances. The entries in table 3.2 for nitrate and N2 point out the the importance of stating the exact chemical form of a substance. When we use mole concept, suppose you read that 1 mole of nitrogen is produced in a particular reaction. You might interpret this statement to mean 1 mole of nitrogen atoms, 14.0 grams, unless otherwise stated. However, what is probably meant is 1 mole of nitrogen molecules, N2 28.0 grams, because N2 is the most common chemical form of the element. To avoid ambiguity, whatever the fuck, it is important to state explicitly the chemical form being discussed. Using the chemical formula, N2 avoids ambiguity. There you go. So what the fuck's it saying? So nitrogen, let's look at the nitrogen has a weight of 14, and if you say N2, that's 28. See that? Say N3, what's 8, 9, 10, 11, 8, 9, 10, 11, 12, and then 3, 42, right? So N3 will be 42. Anyways. Oh wait. So problem number 1. All right, what it says, what is the mass in grams of 1 mole of glucose? So 1 mole has 3 sig figs of C6H12O6. All right, so I just wrote down the problem, okay? All right, so first up, sorry, I'm just thinking real quick. What is the mass in grams? Okay, so first up, let's find out how much carbon weighs. So we got 6 carbon. And I remember on top of my head, carbon weighs 12. All right, and then how much do 12 hydrogens weigh? And hydrogen has a weight of 1. And remember, keep in mind the amount of sig figs, okay? Plus 6 oxygen. Oh, 6 times, I want to say oxygen weighs 16, but I have to check real quick. All right. And this will give me the atomic mass unit of this. All right. So if I'm correct, let's see. This should be 180. This should be I think it's 180. All right. You see that? So let's say 180 grams is equal to 1 mole. 1 mole of this shit is equal to 1 mole of glucose is equal to 180 grams. Okay. So we got one mole of glucose is equal to C6. Man, fuck it. I have to write that whole shit. C6H12O6, right? So 1 mole of glucose, let's put moles, is equal to hold on, guys. Hold on, real quick. I'm all getting stuck real quick, and I shouldn't be. All right, let's keep going. Let's keep going, and then if we get it wrong, we got it wrong. Okay, so 1 mole of uh glucose, so C6 weighs 180 grams. See that? This should be it. Hold up. But calculate the number of moles of glucose. Oh shit. I wrote the problem wrong. No wonder. Wait. Hold on, guys. What problem are we on? I got the problems confused real quick. Oh, I got too ahead of ourselves. They stopped. They just stopped right here. No wonder I was getting confused. Okay, so they just stopped right there. See that? All right, but we're gonna continue. We're gonna continue reading. Uh, damn. Now it says calculate the molar mass of calcium nitrate. All right, so we're gonna go one space back. So calcium nitrate, same shit. NO3, 2. So calcium, it weighs 40 plus 2 times 4. I think nitrate's 14, 2 times 14. And then plus 6 times 16. And when you add those up, you're going to get 164 grams per mole. All right. So all I did was just add that up, and you get 164. And now it's going to look like that. All right, there you go. So we got that so far. So anyway, let's keep going. We got too ahead of ourselves. I was wondering why the answer wasn't matching up, but I think over here it has it actually gave us a number, so that we could actually work with. Because when I was writing this, you see how I'm just converting to grams, but we're just gonna get to the same the weight of the whole thing. I'm going around in circles, and I noticed that, and then I looked at the problem. I said, what was the question? I had to go back. What was the question? All right. So anyways, let's keep going. Interconverting masses and moles. So converting of mass to moles and the moles to masses are frequently interconnected or are frequently encountered in calculations using the mole concept. These calculations are simplified using dimensional analysis as shown in example exercise 310 and 3.14. All right, so let's go. So calculate the number of moles of glucose. So the same problem we were doing, C6, H12, H12, and then oxygen 6. And we have 5380 grams. and they want to find out how many moles. All right. The question is how many moles. All right. So let's go with what we know. So we got 5.380 grams of C6H12O6. All right. And what was it? 180. See that? 180. 180 grams of C6H12O6 is equal to 1 mole. You see that? And then this equals. So what you do is you're gonna multiply all the numbers at the top by all the divided by all the numbers in the bottom. All right, so it'll be 5.380 times 1 divided by 180. You see that? And then you're gonna get the answer I got. What did I get when I did it? All right, so when I did it, I got 0.029. Oh wait. So when I multiplied that number, I got 0.02989. All right, so when I multiplied this whole number, that's what I got. Moles of C6H12O6. All right, that was my answer that I got. That's a 0. There you go. That's what I got. And when you go on the book, that's what they got also. See that? And then it says practice. Oh, damn, guys, look at that. That's a good reaction right there because that's sodium bicarbonate. So if you're in the saltwater community, this is a reaction you want to know right here. How many moles of sodium bicarbonate, NaHCO3, are in 508 grams of sodium carbonate? And the answer is 605 moles of sodium carbonate, but let's figure out how they got that. All right, so and remember, guys, we're only in section 3.4, and we're already doing this is like high school level work now. And like I said, we're doing university level textbook, and we're only in chapter 3. And we're already fucking diving right into the good shit. All right, so sodium bicarbonate, that's a molecule we use in salt water. Sodium bicarbonate. I mean, you don't have to, but it's a chemical found in salt water either way. You know what I mean? HCO3. Okay, so that's the formula for sodium carbonate. And then we got 508 grams of that shit. And they want to figure out how many moles. I think it might be easier to write in cursive. How many moles? How many moles are there? That's the question. You see that? So the answer is 6.05 moles. You can see right there in the book. See that? The answer is right here. But let's figure out how they got it. All right. So first up, we got to write down what we know. We know, well, two things. First, we got to figure out the molecular weight of sodium nitrate. I mean of of sodium bicarbonate. You see that? we gotta figure out the molecular weight. So let's do this first. So one atom of sodium weighs shit. No, I'm a cheat. I'm just gonna look at the notes right there. 23 grams. So one atom of sodium, because all right, let's not cheat. Let's just show you. So when you look at the periodic table, you see that Na, where's Na? Sodium's right there. See, sodium's right here. So right here it says 22.9871 something 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 something. All right. So from right there, all right. So from that weight, I got the number 23. Okay. So one atom of sodium weighs 23. Weighs 23 grams. Okay. Plus hydrogen. There's only one hydrogen. So 1 times hydrogen. I'm just because I memorized this. I know hydrogen weighs 1. Oh shit. What the fuck? Anyways, fuck it. One hydrogen weighs 1. See that? Oh, actually, let's just put 1. Well, actually, yeah. That way you don't get confused. So one hydrogen weighs 1 plus. What the fuck is happening? Hold on, guys. My shit's writing by itself. All right, plus 1 carbon. 1 times carbon. I think carbon was 12. Wait, how much is carbon? Yeah, carbon weighs 12 in the periodic table. All right. Plus, and then I got 3 oxygen, and oxygen weighs 16 when you look at the periodic table. And then this shit equals, when you multiply and add everything, all right, that equals 84. 84 grams per mole. Or whatever the fuck, right? So we got a number right here, 84. Oh shit. 84, right? So we got 84. And then we got this number right here, the one that they gave us, 508 grams. So what you weight on the scale. So now let's get that number, 508 grams that you weight on the scale of sodium bicarbonate, which is NaHCO3. Just so I could fit everything, I'm gonna write it like that. So HCO3, right? So we got that many grams, right? And then so you see we got the grams, right? And then we got the number of grams for the molecular weight. So we got the molecular weight in grams will give me moles. So 84 grams, and then the grams cancel out right there. So 84 grams of sodium bicarbonate. Damn. All right. Fuck it. I gotta probably choose a smaller. Hold on, guys. Let me choose a smaller. Damn, I think it's already as small as it goes. So we got 84 grams, right? So 84 grams of sodium carbonate, NaHCO3, equals 1 mole of that shit. Equals 1 mole of sodium bicarbonate. See that? And that pretty much is the answer right there. All right, so what you're going to do is get 508 divided by 84. See that? And then that equals, when you do the thing, that equals, when you plug it in the calculator, 6.05 moles of NaHCO3. It would equal that. All right. Bam. All right. So converting moles to grams. I think we're almost done, guys. And I'm getting pretty hungry. All right. Yep, we're almost done. Because on the next page was chapter 5. I mean 3.5. All right. So let's go back to reading, and then we'll pull the thing back up. All right. We don't even need to read. Never mind. So calculate the mass in grams of 0.443 moles of calcium nitrate. All right. So like I said, this chemical, you could probably find it in salt water also. Even in fresh water, calcium nitrate. All right. So anyways, let's write down what we know. So they want to find out the mass in grams. So let's put grams is what we want to find out. And then what we know is we got 0.433 moles of calcium nitrate. Calcium nitrate. First, we got to find out how calcium nitrate looks. It's so calcium nitrate is CaNO2. Oh shit. NO3 2. All right. So that's calcium nitrate. All right. So we got 1 mole of calcium nitrate. All right. All right. 1 mole of calcium nitrate weighs how much? So calcium is 40 plus 2 nitrates. Nitrate weighs fuck, how much is nitrate weight again? 14 plus 6 times 6, because there's 6 oxygens. 3 times 2 is 6. Oxygen weighs 16, right? I think it was 6. Yeah, 16. Does it? Yeah, fuck it. Oxygen weighs 16. And then that gives me what is it? Da, da, da. Hold on, guys. I'm trying to figure out if I hold on. Let me check real quick. Yeah, let me check the weight of nitrate real quick. Hold on. No, what the fuck? Nitrate. I mean, no, sodium. My bad. I mean, not sodium. Nitrogen. Yeah, it's 14. All right. So that equals. So what's 40 plus 28? So that's 4. That's 68. 68 plus 16 times 6. Hold on. What is the calculator shit? All right, let's do this. What did I say? 6 times 16 goes 96 plus what is it? Plus 28 plus 40. Was it 40? Equals 164. All right, so equals 164 grams of so 1 mole of calcium nitrate weighs 164 grams of calcium nitrate. All right. And then I think that's where we stop. Bam, right there. Okay, so that's where we stop. So, and then to solve it, all we got to do is multiply all the numbers on top divided by all the numbers in the bottom. So this is going to equal to 0.433 times 164 divided by 1. See that? That should be correct right there. Let's see that shit. Yeah, it looks right so far. So that's gonna equal, when I plugged it in the calculator, looking at my note right there, that's gonna equal, this number is gonna equal to 71.01. Oh yeah, see that's what the book got also. Bam. Now let's compare with the book. Like I said, you always want to compare your answers with the book. And they got 71.1. And it took me forever to figure out the math just because I was too lazy to. All right, so let's continue on. So then when it says practice, what is the mass in grams of 6.033 moles of sodium is it of sodium bicarbonate and 3.0 tenths to the negative 5 moles of sulfuric acid? All right, so let's do that shit. So hold on, let me see this real quick. I don't even know if I did that problem. The part B, sulfuric acid. SO4, some shit. Or HS. Anyways, fuck it. All right, let's do mass in grams. So let's give what the sodium. So this is the problem. NaHCO3. And they want to find out the mass in grams. All right. And the amount we have is 6.3 moles of sodium bicarbonate. All right. And then 1 mole of sodium bicarbonate weighs what was the number? 164 grams. Wait. Actually, you know what? That's wrong. That was for calcium. That was for calcium nitrate. All right, so let's resolve this. So sodium weighs 23. So it's going to be 23 plus 1 plus carbon is 12 plus 12 plus 3 times 16, and then that equals 84. Oh shit, that equals 84. So 1 mole of sodium bicarbonate weighs 84 grams. Yeah, 84 grams. And then that's going to equal. So when you plug this in the calculator, so when you multiply 6.3 times 84 divided by 1, times 84 divided by 1, the number you're going to get is sorry, when you plug that into the calculator, wait, I'm trying to see something real quick. Oh, anyways, yeah. So when you plug it into the calculator, you're gonna get 532 grams of sodium HCO3, sodium bicarbonate. All right, there you go. Fuck. Anyways, I solved that shit, and then if you look carefully on my notes, on the next problem, we got what was it? 3.010 to the negative 5 moles of sulfuric acid, right? And I didn't even do that problem because I didn't know the formula for sulfuric acid. You see that? That's some funny shit. We could do that if you guys want to, guys. We could do that problem. Let me know. Just write down in the comments. But let's just move on because I'm getting tired and I just want to finish this fucking book. I mean, I finished this chapter and we're almost done. See that? Damn, I gotta keep going. All right. So, anyways, guys, this is an easy part in chemistry. So, if you guys are struggling right here, don't really. It takes a while to. Like I said, you guys got to practice it by yourselves. But it does take a while to learn. All right, let's click the new page right there, and then let's open that up. All right, so we're almost done. So interconverting masses and numbers of particles. The number of constant provides a bridge between masses and the number of particles. To illustrate how we can interconvert masses and numbers of particles, let's calculate the number of copper atoms in an old copper penny, such as penny weighs about 3 grams, and we will assume that it is 100% copper. So Cu equals 3 grams, 63.5 grams. Atomic mass unit equals 1 mole of copper. 1 mole of copper equals 6.02 times 10 to the 23 copper atoms. We have rounded our answer, and it equals 3 times 10 to the 22 copper atoms. We have rounded our answer to one significant figure since we use only one significant figure in the mass of the penny. Notice how dimensional analysis provides a straightforward route from grams to numbers of atoms. The molar mass of Avogadro's number are used converting factors to convert grams to moles to atoms. Notice also that our answer is very large. It's a very large. It's a very large number. Anytime, calculate the number of atoms, molecules, or ions in any ordinary sample of matter. You could expect the answer to be very large. In contrast, the number of moles in a sample usually is much smaller, often less than 1. The general process for interconverting masses and numbers of a formula units, atoms, molecules, or ions, or whatever is represented by the chemical formula of a substance is summarized in figure 310. Oh man, that was some weird shit. All right, what are they talking about? Let's just do some problems. Basically, the other thing is that it's pretty easy to convert once you know what you're doing. All right. All right, so it says how many glucose molecules are in 5, let's say write down everything. 5.23 grams of C6H12O6 of glucose. Okay, so once is how many molecules of glucose? So the answer is molecules is what we want to get to. And then on the second question is how many oxygen atoms? All right. So anyways, we got our starting shit. So we got 5.23 grams of glucose, and then we got to figure out the molecular weight. So C times 12 plus 12 times 1 because of the hydrogen. See that? Plus 6 times 16 because that's how much oxygen weighs. And this is going to give me the weight of, what's the molecular weight? I think it's 180 of 180. Okay. And so we got grams of that. So 180 grams of C6H12O6 gives me 1 mole of that shit. All right. And then that's where we get our first answer because we're in moles now. All right. So now we're in moles. And then that's going to equal to 1.75 times 10 to the 22 molecules of glucose C6H12O6. All right. That's the answer right there for part 1 right here. All right. But if we keep going, equals molecules, right? So equals 1. Hold on, guys. Yeah. Equals 1 molecule of this shit of C6. I mean, what was it? C6H12O6. All right. So 1 molecule of that has 6 oxygen atoms. All right. And then now we got the part B. The answer of part B it was just an extra step. And then that equals let's see. Oh, sorry. Oh yeah, that equals I was trying to do the calculation. 1.05 atoms of oxygen. All right. So what I did there was multiply all the numbers at the top divided by all the numbers in the bottom. So when you clear it up, it's going to look like 5.23 times 6 divided by 180. All right. That's going to give me the number of oxygen atoms, which is 1.05 atoms of oxygen. All right. Bam. There you go. And looking at the answer, that's pretty much right. All right. And then the last problem, and we're out of here. All right. How many nitric acid molecules are in 4.0 or 4.20 grams of of nitric acid, HNO3? How many oxygen atoms are in this sample? All right, let's go. Let's write down what we know. So we got 4.20 grams of HNO3. And then the question is how many molecules? How many molecules? And then how many oxygen atoms? Okay. So anyways, so we got the grams. Now we got to figure out how many the grams of moles in there. How many moles and grams are there? So hydrogen is 1 plus nitrate is fucking 14 plus oxygen is 16, and there's 3 of them, so times 16. And then that's going to equal 63. Okay, so 63 grams of what was it? Nitric acid, HNO3. Yeah, nitric acid, HNO3 is equal to 1 mole of this shit. And then 1 mole of this has Avogadro's number, 6.02 times 10 to the 23 grams. 23 molecules. Okay, see that? And then that gives me the amount of molecules. So that's going to equal to, so remember, multiply the numbers on top by the numbers in the bottom. See that? And then that's going to equal to 4.01 times 10 to the 22 molecules. Okay, see that? And then if you want to go get the amount of oxygen atoms, you do the same thing. So we could even just get, okay, there's 2 ways we could do it. We could either do it this way, just grab the final answer from right there, or just keep going. So if we kept going, you see over here, we're just going to keep going. So if we kept going, we're in molecules. All right. And then 1 molecule of nitric acid, HNO3, has 3 oxygen atoms. And then you would have done the same calculation, only multiplied by 3 and still divided by 1. Okay. Okay, but let's take the answer we got, 4.01 times 10 to the 23rd, or was it? Times 10 to the 22 molecules of what was it? Nitric acid, HNO3. All right. And then you do the same thing. So it'll be 1 molecule of this shit has 3 molecules of oxygen. Let me put O2 instead so we don't get confused. Of oxygen, and then that's going to equal to 1.20 times 10 to the 23 atoms of oxygen. And that's how you got that. All right. So anyways, next up is 3.5 empirical formulas and empirical formulas from analysis. All right, we're gonna end it there, guys. I'm already tired. We're an hour and 25 minutes in, and this one's gonna, like I said, from now on, everything's just a buildup of everything we're doing. So if we keep skipping fast, don't worry, because all this we're gonna have to be doing because it's gonna be a buildup. You know what I mean? It's like adding numbers or doing sentences and shit like that. It's gonna be a buildup. All right. So anyways, we're gonna end it here, guys. Much love to everybody that tapped in. I really appreciate you guys. Randy, thank you, and everybody else. All right. So much love, everybody tapped in. I'll see you guys on the next video. And we ended at 3.5. Okay, let's put the bookmark. And we're out.